Yeah, as I was saying, doesn't decrease necessarily, but it's shear thinning. Now, um, now let's go to the problems. So I would read you the problems. Why is the sign on the right hand side of equation 1 negative? Uh, why is this sign negative? That's the first question. What pattern will you get when you compute the shear stress individually for all layers so shown in figure A? This is figure A, and let's say there are 1, 2, 3, 4, 5, 6. For the sake of simplicity, there are 6 volume elements. What will be the pattern that you will get when you start to compute the shear rate or the shear um, um, uh, the shear if let's say shear rate of the at a point at an arbitrary point x in each of these volume elements. What will be the pattern that you will get, when you compute the shear stress also as well as the shear rate? Both are related. In the previous slide, I would like you to match the equation with the type of the fluid that you're dealing with. So basically here there are here there are different types of fluids. Here there are the you know different equations. I want you to match them, 2, 3 and 4. And finally, what will be the effect of temperature on the viscosity of a fluid? Will it be different for different types of fluids? For example, gases versus liquids, and if so, why? So read through these 4 problems, and let's give it another 15 minutes, and then I'll give you the answers. 10 minutes, and then I'll give you the answers. Alright, let's look at the answers. The easy ones first. Why is the sign on the right hand side of equation 1 negative? It's very simple, right? So basically what we are thinking about, what we are talking about is dvx by dy. So the rate of change of velocity, or the shear rate, the rate of change of velocity component x as we move above, to the successive volume element. So the point is it decreases. That is why it is the sign is negative. And here also, this should have given you a clue. The shear rate is defined as minus dvx by dy. That's exactly for this point. I'll repeat this again. As the when there is force applied in the at the bottom of the bottommost when there's a shear stress at the bottommost of fluid element, liquid element of the fluid element, the rate of transmission of velocity with respect to the direction y is successively slower. So that is why the sign is negative. So now coming to problem 2. What pattern will you get when you compute the shear stress individually for all the layers shown in figure A? Or let me put it this way: you the shear rate or the shear stress, which is interconnected. But let's talk about shear rate here. The shear rate, successively decreases, which was the answer to the question 1. Now, if you want to know the the average shear rate or something like that, not even the average shear rate, the sum of the shear rates of into each individual elements, fluid elements, in this in this diagram there are 6, right? Yeah. There are 6 fluid elements. So if you want to do that, what you need to do, simple, right? You just sum the shear rates of all this, and if you know the viscosity of the fluid, you get the shear stress. And the summation is otherwise called as integration. I think you will read more about it, in the successive classes of that you will have, successive lectures that you will see. Coming to problem number 3, in the previous slide, match the equations with the type of the fluid that we are dealing with. Newtonian, I am not given bothered to give it. It's y is equal to mx plus c, so that's why. So what is it for Bingham plastic? Is it 2, 3 or 4? It's 2, right? Because this is called as this is a threshold shear stress below which there is no, you see, if the shear stress is below the modulus of the shear stress is below, this is called the yield the stress yield. The threshold shear stress is called as the yield stress, and if it's below or down naught, the dvx by dy equal to 0, and that's why it's 0 till here, and after that it more or less behaves like a Newtonian fluid. This is for a Bingham plastic. And what is for a power law? This is the equation for the power law, right? So if n is greater than 1, that's why I told you, I gave you the answer that I should have deleted this. If n is greater than 1, the power law behaves more parabolically or pseudo exponentially, and if n is lesser than 1, depending upon how less it is, it behaves in a flattish manner. So that is a pseudoplastic fluid, and this is a dialent type of a fluid, or shear thinning fluid. So what is this equation? This equation is actually I just kept it so that you could think about it. Not about the equation. Think about match everything. It should not be like 1:1, so that at least you should have the understanding of the graph and try to match the graph with the equations. Matching graphs with equations, if you get that art, you solve much of the problems typical people face in science. So nevertheless, equation 4 is the Cartan model for the equation of blood. So what does blood contain? Blood contains a plasma where it has the proteins and a bunch of stuff, and also it has the various types of cells called as erythrocytes and stuff like that, erythrocytes, leukocytes, etc., etc. And one thing that you could see here is common that is in common to the above Bingham plastic is fluid is the yield stress, the Downot. The Downot term is here, and this Downot term seems to be correlated with that of the amount of erythrocytes that are present in the blood. And however, what I'm saying is a very oversimplistic as a representation of the Casson model. In fact, there is a field of study for understanding the various aspects of the rheology of blood and the various crucial implications that it has on human physiology and human healthcare. So I just put this equation to confuse you. I hope you were not confused. That was the point. Now, finally, even if I want to confuse you, you should not be confused. That is the point. Now coming to problem 4, what will be the effect of temperature on the viscosity of a fluid? Will it be different for different types of fluids? Yes, it will be different for different types of fluids. As the temperature increases, the viscosity increases for gases, and as the temperature decreases, it decreases. But let's keep the temperature increase in focus. So as the temperature increases, the viscosity increases for gases, but for liquids, it decreases. Now, why that is the case, I will leave that that question open for now. However, I will give you a clue for the interested people to find out. There are two types of forces acting here that modulates the viscosity as the temperature changes. One is the inherent kinetic uh, velocity of each molecule, and the second thing is the change in the cohesive force that is present in the fluid. Now, what is the balance between the two? Whether there is a cohesive force in gases, and if not, is that the reason? And why does the cohesive force? What happens of the cohesive force that we are talking about for incompressible fluids? I would let you to think about it. I would like you to think about it, and I will give you the answer in the next lecture. So that's all for today. I hope you enjoyed my lecture. Thank you very much. Bye bye.